Okay, so welcome to day 3 of the North American Einstein Toolkit workshop. Our first speaker today is Wolfgang Tichy, who's going to talk about numerical relativity with Nmesh. So Wolfgang, take it away.
Hello, good morning. Thank you very much for inviting me. It's nice to talk here, even remotely. So yeah, as you just said, I'm going to talk about numerical relativity with Nmesh, and this is work that basically we have been doing at the FAU group. That means that's me and a couple of former postdocs and students and also current students. So they're listed here. Well, here's a plan of the talk that I want to give. I want to first talk about the discontinuous Galerkin method that we use in Nmesh. And then I talk more about mesh refinement and parallelization, and then specifically about GRHD in Nmesh, because we want to sort of focus eventually on neutron stars. And then I also show you some neutron star examples. And then we don't want to use only the DG method, but we also want to use something like finite volume at this together. And I will talk about how we want to do that or how we are doing this. And also I show you some results like how this can work, for example, with shock tests. And also I show you some work towards evolving neutron star binaries, because that's what we want to do at the end. So this is the idea of what I'm going to say. And so here's now the first part. So by the way, there is this bar on the top of my talk that I don't know how to get rid of. It probably covers the headline. Is this the case for you as well, or just for me?
We don't see it.
You don't see it. Okay, then fine. I don't worry about it. Okay. So I want to talk about like the motivation of why we want to have something like Nmesh, which is a new code, right? Here in our group, we traditionally have used the BAM code, which is somewhat similar to Cactus with Carpet. And BAM actually works pretty well. It can involve black holes and neutron stars, and it uses finite difference and finite volume methods. And as I said, for now, it works and does the job for us. And the way it does that is it has sort of a boxes within boxes mesh refinement. And in total, it usually uses about 2,000 boxes, typically for 2 neutron stars, for example. And the way then things are parallelized, when you have only like 2,000 things, you need to cut it into more pieces to have something for parallelization to work. And the main strategy there is to subdivide each of the boxes that we have into smaller sort of sub boxes, and then divide out these sub boxes to different MPI jobs, and then these MPI jobs have something to do. The way this is done with finite differences is that ghost zones, many points deep, need to be added to each of these sub boxes. And then via these ghost points, the different boxes communicate with each other. The problem is after you divide often enough, that means if you use enough MPI processes, then you have you get more and more sub boxes, and each time you add these ghost points, and it can be that if you add too many, that you have more ghost points than actual computational points, and then basically the communication starts dominating your calculation, and then it's no longer efficient and doesn't scale very well. And so this is a limitation that BAM has. I'm not trying to say anything bad about BAM. It's a good code. It's just this is an inherent limitation. And I should say that because this is about Cactus, what you guys are doing at the Einstein toolkit, like the same actually would apply if you use Cactus with Carpet. So for that's basically so we have here some sort of problem and we want to get around it, and that's the motivation for like doing something new. And so the goals for our new program, that is Nmesh, we want to cut down on this communication overhead and use more parallelization. And also we would like to use, if possible, a numerical method that's more accurate than just finite volume or finite differencing. So that's the idea of why we want to do something. And now I want to talk about the DG method that's within Nmesh, which is sort of the main numerical method we use. Yeah, this is this discontinuous Galerkin method, and for this method we use these unequally spaced Gauss-Lobata grid points. And in order to discretize an equation, we then integrate against Lagrange characteristic polynomials. And here is an example for a PDE that you might want to discretize, but this is just a one-dimensional example, a simple thing. This PDE here. And if you go and integrate against these polynomials and go through the derivation, what you end up as a discretization is the line below here in blue. And this is a discretization in a certain interval. That means this is in one element. Instead of this field U, you now have Ui, which is U at a particular grid point. I labels the grid point. And instead of the flux F, you then have Fj, which is a flux at grid point J. So basically the left-hand side looks pretty much like before. The only difference is instead of derivative operator, you now have a differentiation matrix, which is some sort of full matrix that you can calculate. And the only difference is that on the right-hand side now something appears. And what the main thing that's important here is there the numerical flux F star appears. And that's a thing that you use to either impose boundary conditions or to couple different elements together if you have several. And the idea is, of course, to have more than one. We want to actually use many. And here's an example how this would be done. There's a blue element on the left and an orange element on the right. And they sort of overlap at one point. At this point, I would say both elements have this point, and at that point the numerical flux has to be calculated. And for example, you could use the LLF flux, and this way they exchange information. So if you have, I don't know, a traveling wave or something, that it can go from one element to the other. And the advantage of this method is that you need communication only at this point, and you don't need to add any extra ghost points. So there's less communication inherently for a DG method. And so this what I just shown is just the spatial discretization. And of course, you then also have to discretize in time. And there you can, for example, use a standard Kuta integrator or something like this to just go forward in time. And the advantages of the method are then that this can be parallelized with less overhead than when you compare to, I don't know, finite differencing or finite volume, because you don't have extra ghost points. And also, it is much more accurate for smooth fields, right? It's basically reaches spectral accuracy as long as your fields are smooth, right? If they're not smooth, then not. But sometimes fields are smooth, and then it has an advantage. All right, so this is sort of the basic method we want to use. And then, as I said, we need many elements, right? Here I just shown two. And of course, we want to do this in 3 dimensions. So we actually have adaptive mesh refinement. So what this means, when we do simulations in 3 dimensions, we introduce a number of patches, or each maybe with their own coordinates. And then we start dividing those further, subdividing them. And this is the way we get lots of elements. So what's shown here, or I should say, how is this division? How does it happen? Well, imagine you have one of these patches, and now you can cut it in 2 in all 3 dimensions. So you basically cut it into 8 child elements, and this way you get more elements and also more resolution. And you can keep going and do it again and again. And here's an example of this. This is where we started out with 4 cubed sphere patches in the XY plane, and then we refined twice. And this is how we get all these many patches here, or these many elements, I should say. And in this case, these elements have, I don't know, 8 by 8 points each. And in fact, this is from a black hole simulation where we evolved the GH system to just do a single black hole with excision as a test case. And this is when you sort of equally refine everything. It looks like this, but you can also do, because this can be adaptive, this mesh refinement, you can refine wherever you want. And what's shown on the bottom picture is basically like an example of what you could do with a neutron star, right? In a neutron star, you have a star surface. And at the surface, the matter field, like the density, has a kink. And so it's not smooth, and maybe you want more resolution there. And that's exactly what happened here. You had these elements, and some of them have been refined more than others. For example, there's little resolution here outside the star, and inside the star is also less resolution. Then around the star surface, these elements have been refined more. And so that's what you can do also. And technically how this works is that Nmesh uses some sort of oct tree to track the refinement. And each leaf node in this oct tree corresponds to an element. And each patch then starts with one root node, and that then covers the entire patch. And then this root node or this root element can be refined as much as possible. And just one moment, I forgot one thing here. Where is my window? Okay. I guess I don't have the most, it doesn't matter. Okay, so this is about refinement. So we have adaptive mesh refinement. And then we also need to parallelize this, right? And as I just said, we can, I don't know, do this refinement over and over as much as we want. And typically when you do this a lot, then this AMR that we have in Nmesh leads to hundreds of thousands or even millions of elements. And that means we have all these many elements, and that's then the strategy to parallelize. We then divide these many elements among the available compute cores. And typically what you want many more elements than compute cores. That's when this thing works best. Now, in terms of actually then parallelizing, there's a few more tricks one can use. It turns out that you need to compute derivatives. I already told you about these differentiation matrices that you have to take derivatives that appear in your PDEs. And it turns out that these derivatives can be taken locally within each element. So you don't need any ghost communication at all, or any communication to just compute a derivative within one element. And so that's a good thing, and we take advantage of this. The only thing that needs to be exchanged between elements are these surface fluxes, like at that one point where they touch, or at that surface where they touch if it's 3 dimensions. And currently, Nmesh uses MPI plus OpenMP for parallelization. And the work done in each element for one time step then includes the following things. So we start by sending these surface fluxes to the adjacent elements, right? That's because every element needs to have this. So we start sending them and also receiving them. But then while this is happening, we don't wait for this to succeed. We already can calculate something. And the thing we can calculate is we can take all these derivatives or anything else that can be done locally. And most things in this method can be done locally. And then then this calculation happens, and after the calculation is done, then we look and see if we have received the fluxes, and hopefully by that time we have actually received it. So the idea is that we can overlap communication and calculations to sort of make it more efficient. What Nmesh can also do, if there are enough compute cores, you can also launch OpenMP threads, right? You can launch a certain number of MPI processes if you want, or jobs. And then each job can still launch OpenMP threads. And the parallelization strategies, they're the same. These elements that you have on an MPI process are then divided by the OpenMP threads. Okay, and so then the whole thing actually works relatively well, at least in this test case I'm showing here. This is for the evolution of a single neutron star, where we have divided our mesh into about 250,000 elements, and each element then uses 5 by 5 points. And what's shown here is essentially the speed up for a certain number of cores. So the straight lines here are sort of the ideal speed up that, it should be like this. If you increase the number of cores, it gets faster in a linear fashion. And here what we show is the results on 2 computers, where it actually sort of more or less follows this curve. The squares are for the Bridges 2 computer, and you can see when you increase the number of core, the speed increases, and the same holds for the other computer, the one shown here in blue. And in fact, in this case, we get almost perfect scaling, and it depends a bit on the problem. And this is a strong scaling test, I should say, but there's a certain problem, and we just increase the number of cores and don't change anything else. Okay, so the next thing I should talk about is then, since we want to do neutron stars, and I mentioned it already that there was a simulation just now, that how we do this? Well, we use the sort of so-called Valencia formulation. And that means we have certain evolution variables. They are called here D, tau, and S, which are mass density, energy density, and momentum density. And these are the variables we actually evolved. These are so-called conserved variables. And those are related to certain primitive variables like the pressure or an energy density or 3 velocity, things like that. And the evolution system then looks like this, just like we mentioned before, that we have a vector of variables that we evolve, and this is exactly this D, tau, and S, and a flux for them, and also some source terms. And once an equation of state is satisfied, is specified, I should say, once we have an equation of state, we can then also recover the so-called primitive variables, which are a local mass density and energy per particle, a free velocity, and a pressure. They can be recovered if you have an equation of state, because if you count carefully, these are 6 things, while the evolved variables are only 5. So you need to give this also this equation of state to be able to sort of close the system. The only unfortunate part about this is you need a root finder to do that, right? This cannot be inverted analytically. But we follow this method by Galerkin et al., and it actually works relatively well, except for some problems that we have, and that probably everybody has had. Because this root finder, or this inversion procedure that you go back to your primitive variables, which you do need, this works only if the fields that we evolve are physically reasonable. For example, this evolved mass density should be positive, and the evolved energy density should also be positive. And there's also a relation on what the momentum density should be. The problem is that these relations that should be true are not exactly enforced by the evolution equations. And especially numerical errors can violate these. So it can happen that when you evolve for a while, that suddenly the mass density becomes negative at one point or something like this. And then we couldn't recover the primitive variables, and we have a problem. I should say this happens mainly in low density regions. Like if the density is high enough, that usually does not happen. And the usual cure, that what most people do, you can add an artificial atmosphere to sort of raise the density to a certain level everywhere, even outside the stars, so that the hope is then that the density never gets that low that this problem occurs. But the problem with the DG method is a bit worse, because when the fields are not smooth, for example, at a star surface where you have a kink, a DG method can lead to sort of Gibbs oscillations, that sort of up and down oscillations, and then your density can easily dip negative, and then or other fields too, and then the above conditions can actually be violated. And the usual cure for that is, and that's something we actually do need, is we have to use certain limiters. And I wanted to say something briefly about them as well. So we use a certain set of so-called, that we call positivity limiters. The idea is to keep certain things like the density positive. And what we actually do, we use mean preserving limiters, right? In each element, you have, you can take the volume integral or the mean over any sort of field. And if this, for example, is a matter field, if you integrate over the density, you get the mass in the element, and you want the mass, of course, to be conserved. So we want the mean of the field to be preserved when we change anything. Right? So we now have to apply a limiter, and that means we need to change something, but we want to change it in a way that we don't violate mass conservation. And this blue thing here is the equation that we use for it. We basically scale towards the mean. This U bar is the mean within an element, and U is whatever U is at each point. And then there's a variable theta that we choose as close to 1 as possible. But we have to make it, if there's a problem, we have to make it maybe lower than 1, so that we can basically make every point approach the mean in the element. And that means like points where it's very low will be pulled up, and then you can get them positive this way. And we do the same thing for all evolved variables, right? For the d, for the tau, and also for the s. And for the d, we also put in some, we say basically that d should be positive everywhere. So this is basically almost like an atmosphere. We say that this value, that d should be larger, then we make it sort of 10 to the minus 12 of the maximum density that we have, but the maximum is usually like in the center of the star or something like this. And this works actually in most cases, but it could still fail if the density average turns out to be negative. But if you have a lot of points where the density is negative, it could be that if you take the average, that the whole average is negative. And if you scale towards the average, you're still not making everything positive. And then this positivity limiter can fail, but that doesn't happen too often. So we use it whenever it works. And if it does fail, then we do, in addition to that, we do pointwise fixes. That means we increase d or tau or decrease s as needed at each point. These latter changes, if we make it pointwise, they would violate conservation laws. But what saves us here is that this doesn't happen too often and at very many points. The last thing we need to do to deal with these Gibbs phenomena is that we also have some filters, and we use these so-called exponential filters, which means we expand our evolved fields in Legendre polynomials, and then we get the coefficient of each polynomial, and basically we get a series of coefficients, I call them CL here, and then we scale each coefficient with a certain factor. And what basically is done, this is an exponential filter. That means we basically filter the highest coefficient a lot. That means that one gets suppressed, gets made smaller, and the others are basically untouched. That's the filter we use. Basically, so we filter the highest coefficients. That's how we choose our exponential function here. The last thing is that we have implemented an artificial atmosphere like people usually do, but we don't actually really need it. It's enough if we have this limit. So we have done evolutions without the atmosphere, except for this positivity limit, which is sort of like an atmosphere too. It keeps the density positive. But it's not as strict as an actual atmosphere, this relation alone, right? It's just only this. And it could be helpful in the future, like we have seen with evolutions in BAM, that an atmosphere can interfere with certain quantities in your evolution. For example, if you're interested in ejecta, after a merger, it could be that if you have an atmosphere already, that the ejecta, which are small, they could be sort of swamped a little bit by the atmosphere, so it gets less precise. And so if you can avoid having an atmosphere, it could be actually good. Okay, and then we did some tests to see how this all works in Cowling approximation. That means we evolved the matter fields, but not the metric. And this we do for actual TOV stuff. That means this is a static solution. It's just a test case. Nothing should actually evolve. But of course, numerically, things do change when you just do numerical evolution. And what's shown here on the top left is the central density versus time for 3 different resolutions. So the blue is very low resolution with 4 levels of refinement, and then the orange is 5 levels of refinement where you get more elements, and then the green is even more refinement. And you can see that the central density of the star, like at low resolutions, it varies a lot. This gives oscillations that actually do occur, sort of make everything oscillate. Then if you increase the resolution, it gets better and better. Right? And I should say this is done with pure DG. But we can sort of stably evolve in each case. And as I say, if you have enough resolution, it actually gets better. And you see still some wiggles in there. And these are basically, there's oscillations in there, like these sort of higher frequency oscillations that you can see. And we check the frequency of these. They're actually with the correct frequency, right? Such a neutron star, like when it just sits there, if you hit it, it will oscillate with a characteristic frequency. And this is exactly this frequency. So the frequency comes out correct. And the reason why it oscillates is basically it's excited by numerical noise, right? So analytically, it shouldn't do anything, but then there's numerical errors and they start exciting this oscillation. What's also shown here is the rest mass conservation, right? So this is the total rest mass, how it changes over time. And at least for the high resolution, it doesn't change very much. For the medium resolution, it changes more. And so you can see that the rest mass conservation gets better when you increase resolution, as it should, and it's actually quite good at high resolution. What's also shown here is the volume integral over the kinetic energy, also versus time for the different resolutions. And again, what you can see in this one is you see the oscillations, these sort of higher frequency oscillations quite well. And as I said, they have the correct frequency. So what we can say here, we get lots of fluctuations at low resolution, but as long as the resolution is high enough, we can actually do neutron stars with a DG method alone. So in that sense, the method works. And this was just a test to sort of verify this can actually work. Okay, so the next thing I want to talk about is, so it does work, but we have these oscillations that are, at least at low resolutions, quite bad. And for that, we would like to incorporate also finite volume and finite differencing methods. The idea is that maybe if you're in a region where there is just, where the fields are really not smooth at all, maybe in a shock, then the DG method might not perform very well. And so that means we want to switch certain elements to finite volume or finite differencing. And the idea is in Nmesh, you want to keep the parallelization as it is. Therefore, we would like to not have more ghost points. And the way we do that is, this is again an illustration how we do it in 1D, right? So on the blue element on the left is a DG element, and the green element on the right is also a DG element, in the sense that these elements have these unequally spaced Gauss-Lombardo grid points, while in the middle, the orange element has equally spaced grid points. And this is where we intend to use finite difference or finite volume. But we don't add ghost points. We just have these endpoints where things sort of meet, just like in the DG method. And then we, in this orange element, where we want to do, say, finite differencing, we use essentially almost the same discretization as for DG, right? Remember, if you have an equation in 1D that looks like this, the discretization in DG was that, and we use that form of the discretization also for finite differencing. The difference is that this differentiation matrix that appears here for finite differences is now, it actually becomes simpler, and it has a lot of zeros. It's just near the diagonal you have entries. The only sort of slight complication is that this differentiation matrix now has to use one-sided stencils because we don't have ghost points. But that is something you can do with this matrix here. The other thing that changes, these weights that appear in here, they change a little bit. They have different values for a finite differencing method. But everything else is basically like it was in a DG method. And that means it fits very well into the scheme we have already. And this is what we will do if we want to use finite differencing in an element. We may also want to use finite volume in this orange element. Then we discretize a bit differently. Then we discretize like you normally would discretize for finite volume method. Basically, what you do in order to approximate the derivative, you take the difference between fluxes at midpoints, right? So here we have these orange grid points, and in between are the midpoints. Like if this here is grid point I, then the midpoint that is denoted here, say, is I+1, is the one in between. And there's I+1 and I-1. These are the points to the left and to the right of my actual grid point. And there we need the so-called numerical flux. And this flux has to be sort of obtained somehow because you don't have data initially on these grid points, on these midpoints, I'm sorry. But we use standard ways to reconstruct these fluxes. For example, VNO3 or VNO5 can be used. At least they can be used in the interior of the element. The problem is when you get close to the boundary, these VNO stencils are too big and don't fit in anymore. And there things get more tricky. But what we basically do, that we fall back on lower order methods. So that we don't need to introduce ghost points, right? Because we do not want them. And the advantage of this whole thing then is that the communication between elements still occurs only at the endpoints. No extra ghost zones are needed. And that cuts down on communication. And even more important, maybe, if we need communication only between nearest neighbors. If you do this in 3 dimensions with arbitrary shaped domains, if you were to use regular or traditional finite volume methods, it can happen that you need communication between next to nearest neighbors even, and that we can totally avoid here. Okay, and so then of course we need to test this, and what's shown on this slide is simply a test in a simple case. There we evolve a smooth scalar field, but we now add these regions where we have finite volume just to test it. And in particular, here's the mesh in the middle. This is a cube in the middle of the middle cube here. Maybe you can see that the grid points are such that we have equally spaced grid points, and there we use finite volume. And in the surrounding cubes, we use dg. Right? And we basically evolve this scalar field on this 3 by 3 square. Actually, it's from -3 to +3. And then what's shown here is like the evolution at a certain point. And what we do, we basically impose the analytic solution, which is some sort of sinusoidal wave entering through the boundary, and then we evolve it here numerically to the middle of the domain. And we can do this at different resolutions. That means with different orders of refinement. And that's shown. What's shown here on the bottom plot is the error versus time when we use different resolutions. More and more refinement. And you can see that the error goes down. That means it's converging. That is good. And if one looks at this, one can see that the error decreases by about a factor of 4, which means we get second order convergence, which is sort of the method that we applied. What we were trying to do in this particular finite volume method that we have constructed is supposed to be second order accurate when you have smooth fields. We have repeated this test also in 3 dimensions. This is actually on a square, and you get the same result, that it is actually second order convergent as long as you have smooth fields. If the fields are not smooth, if you have an actual shock, then for shocks you don't necessarily get second order convergence. That's a general feature of finite volume methods, and that's something we cannot improve upon. And in order to just make sure this works, we have also done some shock tests, some shock tube tests, where you start out with a density profile like this, that you basically have a discontinuity in the density, and you have also discontinuity in the pressure, and the initial velocity is 0. And we have evolved this with both pure dg and also with this finite volume method that we have. And for the dg case, we have used 200 elements in this region here with 4 points in each element. And for finite volume, we have done it differently. We have used sort of 25 elements with 32 points in each element. And then we just evolved this, and after a certain time, sort of features evolve in, say, the density, this kind of feature, or in the pressure, or in the speed. Yeah, so this is basically shown after a certain time versus x, how these variables look. And the different colors that are shown here are for different methods. There are 2 dg methods we have used and 1 finite volume. And when we zoom in into this sort of difficult to resolve feature here for the code, then in blue we show the analytic solution. In red is the finite volume method result, and then the orange and the green are results for dg. In dg, I should say, in order for this to work at all, we need extra limiters on top of the positivity limiter, and we use a limiter that has been developed by Mo, Rosmanit, and Seal. That basically just when you get Gibbs oscillations that are too strong, it scales back towards the mean as well. And these limiters, they make it possible to actually evolve shocks with dg. Just one should say that indeed the dg results are not quite as good as the finite volume results. So that's the reason, the motivation why we actually want finite volume. So we can say that the finite volume works altogether better than dg when you actually have a shock. But it's not that you couldn't use dg at all. It's just it's not quite as nice, the results. That's what I should say. And the 2 different dg results are simply 2 different limiters. Like one limits the primitive variables and the other one the conserved variables. And the one that limits the primitive variables does a little bit better. We have also, so this was in 1 dimension. We have also done it in 2 dimensions. And again, you start up with some sort of discontinuity here, where you have a high density region here, a low density region here, and some sort of intermediate density. And then you evolve this, and you also have velocities and pressures. You evolve this with 100 by 100 elements with 4 points to cover each to each of them. And you can do this with the DG method, and you get a certain result. And it looks like, if you study the literature, it looks sort of like what you should get. You can also do it with the finite volume method, and it's just a little bit sharper. It looks a bit more than what you should be getting. And again, so what I can say here, that the finite volume method does a little bit better than the DG method, and that's why we would like to use this. Okay, we have done another test where we have a neutron star, and this is now no longer a stable star. Here we start with an unstable configuration. That means analytically, this is a solution that's sort of overdense, and the analytic solution is actually metastable, but if you perturb it in any way, it will expand rapidly and then contract again and oscillate. And that's sort of what our numerical solution does here. The numerical errors actually perturb it, and then it starts. At first, you have a high density, and then it expands. The density becomes a lot lower. There's the central density shown here versus time. And then it bounces back, and you get these wiggles here. And what we show here is for different resolutions with different number of grid points. And we use finite differencing and finite volume here. And this is no longer Cowling approximation. Here we also evolved the gravitational fields. Yeah. And we expect these sort of violent oscillations that we expect in this configuration, and the code can actually handle them. So this is a test that tests our finite volume and finite difference methods, just to make sure that they actually work. And then I should say more about how we actually do this, right? So this was done with general relativistic hydrodynamics. I already said we want to use the Valencia formulation, but we also want to evolve gravitational fields. And for this, we use the generalized harmonic system. And in this case, for the generalized harmonic system, the equations are of this form, which means they are actually not in flux conservative form. You don't actually have a flux for these equations. You have some sort of matrix multiplying your derivative terms, the principal terms. And this kind of equation can be treated with the DG method or with the finite differencing method we have talked about, but not with the finite volume method. Yeah. So, and this is why we also need the finite differencing method. The finite volume wouldn't work on that equation. We also have the hydrodynamics where we use the Valencia formulation. I said this already, and those are actually in flux conservative form. So here we can use either the DG method or the finite volume method, and that's what we do. And so now we have a choice. We can use either DG or not. And for this, we have some sort of trouble score to indicate the elements where we have non-smooth fields. And there we maybe then want to use, not use DG, but rather use finite volume or something like that. As the idea is, if an element is smooth, we use DG for both the gravitational fields and the hydrodynamics. But if it's not smooth, then we use finite differencing for the gravitational fields because the equation allows for only that. And we use finite volume for the hydrodynamics. Okay, and then as I said, there's a trouble score that we use to make these decisions, and I should now describe roughly at least how these trouble criteria work. We go through a list of criteria and check, and then we decide is the other field smooth or not in an element. And we basically say that there is trouble, that means non-smooth, if certain things happen here. They're listed here. For example, there could be trouble during the evolution, meaning that we needed one of these positivity limiters, for example, right? If we need a limiter, then probably something happened, and then we say, okay, there's trouble. We try to detect star surfaces, and that means if the density is within a certain range, right? If it's between 10 to the minus 6 and 10 to the minus 1 of the maximum density, then we say in this region is a star surface. That means it's non-smooth, and therefore we should signal trouble. We also look at during an evolution step, do our fields change a lot? If they change a lot, then there is probably trouble, maybe some Gibbs oscillation. And the way we do that, we basically compare to the minimum and the maximum on the previous step with an extra added or subtracted. And here it says this, we do that after each time step, and we look at the previous step. That means we subtract delta t here. And the U that I'm talking about are the evolved fields, like this would be the matter fields for the Valencia formulation. And this minimum here, for example, is taken over all neighboring elements at the previous time steps, and the maximum as well. This is a method that you can read up of. Dubs et al. Have sort of developed that. And so that's one indicator we look at. We also look at the Pearson indicator, which is yet something else. We basically compute, again, the coefficients when we expand in Legendre polynomials. And we take a ratio between the high coefficients and all the coefficients. And you can always imagine, like, if the high coefficients are large, then you have high frequency noise. So if this ratio gets large enough, then we say we have trouble also. So that's our last trouble indicator that we have, right? So And if any one of those basically says there's trouble, then we say there's trouble, and then we should probably use finite differencing or finite volume. Yeah, so basically, we say that there's no trouble if none of the above occur, and so then we might be able to use the DG method. And we also say there's no trouble if if we are in a very low density region, right? In these low density regions, you might actually have violent oscillations in the matter fields, but if they are low enough, say below 10 to the minus 6, then we really don't care about them, right? So if the matter oscillates a little bit at very low density, it doesn't really influence the gravitational fields very much. So, and the reason why we do that, why we basically declare no trouble and therefore force the use of DG, is that DG is actually more efficient. So we want to use DG in most of the domain where there is no matter, where the space is empty or mostly empty. Okay, so this is how we sort of trouble, we signal trouble or not, and then we can decide if we use DG or not. And this is sort of, I quickly saying it here. Here is how we switch between the two, right? So then you have to decide how you actually switch. You have now an indicator that tells you when to switch, but now I'm going to say a few more words of how we switch. And in this text here, the FV stands for either finite volume or for finite differencing for the gravitational fields. And the way we decide if we now need to switch is that we take a Runge-Kutta step, and then if it's troubled, according to our trouble indicator, then we do something. So if you have been using DG, then we say we should now switch to finite volume. But we don't just switch, we also then redo this time step. Because if we have taken a DG step and there was trouble, then we have maybe large oscillations in the area. We don't want them. So we basically go one step back, and then do it with finite volume. If you have been using finite volume already and there was trouble, well, then we just keep using finite volume and don't really change anything. If it's not troubled, according to our score, and we have been using DG, well, we just keep it on DG and say, okay, things are going fine. But if it was finite volume, but we figured out that there was no trouble, then we switch to DG now, but we don't need to redo the step. We just use DG on the next step then. The advantage of this scheme is that we use any region that's non-smooth, right, where we have trouble, will be always evolved with finite volume, which is similar to what Depe et al. Have been doing in their code. And this way we can avoid Gibbs oscillations entirely. Well, entirely if the trouble score works perfectly, which maybe sometimes it doesn't. But as long as it works well, we can avoid them. Here's now an example where we evolved two neutron stars. So there are snapshots of the stars when they start out here and then they start orbiting. This is just shown like doing the in-spiral at different times. And the reason why I'm showing this, I want to show you what the computational mesh does in this case. So this is for the evolution of two neutron stars, and in this case, it's actually equal mass stars, and we evolved them with the MPA1 equation of state. So this is the full thing with hydrodynamics and gravitational field, everything evolved. And we also use our AMR to sort of do refinement near the stars and not anywhere else. The way the AMR works, we there are two spheres that track the stars, and in that sphere we have very high levels of refinement. We actually refine 5 times. So this is this refinement I was talking about. We split the elements in half 5 times. And then when we go away from the star, this high resolution drops successively. The further you go away, the less refinement you have. And you kind of see that here, there's a lot of, well, this here, I should say, this is a wireframe mesh of the grid. And as you go away from the stars, you see that the lines are further apart. That means you have less resolution. So away from the stars, it drops. This is the AMR doing it. And as I said, it's actually adaptive. It simply follows the star centers. It sort of has refinement somewhat similar to what maybe BAM or Corpet would be doing, except it's not box-based refinement. It's sort of, if you're within a sphere, then the elements are refined. And what we do in each element, when it's finite volume, we use 12 points, and when it's DG, we use 6 points. The reason why we use more in finite volume, because we expect that maybe there is some sort of non-smooth feature that maybe needs more resolution. So this is the AMR, but on top of the AMR, as I said, we have the switching between the DG and finite volume. And then the picture also sort of shows, because in the stars themselves, on the inside of the stars, the fields are actually smooth. And this is why this looks different here, the wire frame. Because in the stars, we use DG in the middle because it's smooth there. But we have only 6 points, while if you go towards the surface, we use finite volume, and there we use 12 points. And that's why the mesh looks finer here. Right? The element sizes are the same. The elements are have the size of one of these little squares here, out here too. But they have more points, and that's why the lines are denser. So what one can say here is that our trouble indicator has worked in the sense that it switches to dg inside the star, but switches to finite volume around the star, I mean at the surface. And what you should also say, all elements away from the stars, like say out here, they have switched to dg because they detect there is basically no matter, and therefore they will use dg. And this is at an evolution stage where the stars are somewhat close already, where there is matter in between the stars that's very non-smooth, and there it has decided to switch to finite volume. And so this is what this here shows, that actually our method can do the AMR, and it also can decide where to switch, and the switching seems to work, at least it's satisfactory. But it's maybe not ideal yet, but it's satisfactory. And it's sort of dynamically tracking the stars. All right, this you can imagine this is moving. I'll show a movie in a moment. And I should also say this is shown here in a sort of logarithmic scale. So you see matter outside here, but it's sort of low density. Okay, and then we did this evolution. This was just for the in-spiral, and we did it with 3 different resolutions. Like the picture I showed you was with 4 levels of refinement in each star, but we can also go to 6 or to 4. And what's shown here is sort of the mass conservation. When you now transfer information from dg to finite volume elements, there can be violations of mass conservation, but this converges away nicely. So you did get good mass conservation at high resolution and less good at medium, and so on. So basically, if you go to high enough resolution, you shouldn't worry too much about the mass conservation. That's really what this plot here says. Okay, and this was just for a short test evolution for the in-spiral. We have redone this run for a longer evolution. And basically here I should say we have in the finite volume elements, we now use 24 points, and in the dg elements, we now use 12 points, which means we have 2 times 24 plus 5 times 12 points across the star, which this is a decent resolution. And I have a movie here that I want to play briefly. So I should maybe stop it. So the stars start out like this, and I'm here mostly interested in what the stars do. So you can see here these are elements that have 12 points here in the middle. This is where it has switched to dg. And then near the surfaces, it has switched to finite volume. And again, this is a logarithmic scale. And this is the initial configuration where there's nothing outside the stars, essentially. But during the evolution, there's, this happens in all codes, that a little bit of material leaves the stars. And so you will see something outside the stars as this goes. So let it go now. And what you can see is that it sort of nicely tracks that they should be using dg inside the stars, but not near the surfaces. And then, of course, at some point, the stars start touching and merge. And if I, okay, I guess I missed it. So as it tracks this nicely, but when the stars merge, you can still see that when they touch, that it still uses dg in certain portions of the star, right? So maybe right about here, they start touching. And you can see there's regions where stuff is still smooth enough to use dg, but not near the surface of this newly formed sort of compact object. And then, this, and the movie just repeats. And what I have here is some snapshots. The top snapshots is sort of after merger, but they are touching, and you can see it's using dg in certain regions. And then as this merges more and more, the region where it can use dg is less and less, because there are now shocks in there. And at the very end, the last frame, we use almost no dg anymore. We use almost everywhere finite volume, but that's sort of expected because you have shocks. Also, I should say, in this simulation, the masses are high enough that this is actually forming a black hole, right? So this is shown here. This is the central density versus time. And at the end, it shoots up. That means a black hole is forming. And our program stops here because we haven't, we don't have the ingredients yet to make the generalized harmonic system work with a black hole, right? We would need to now switch on excision or something like this, which we haven't done yet. In fact, our plan is to later not use the generalized harmonic system, but use something close to Z4 so that we don't have to use excision. What's also shown here is the star track. So you see it's reasonably non-eccentric. And this blue line is the track of star 1, the orange line is the track of star 2, and you can see they come together, this merges. And basically, the message of this slide is that during the in-spiral, that the tracker works well, and we use dg where we want to. That means inside the stars. And even, and also away from the stars, is probably not very visible here, we again use dg for most of the space. But this is a zoom in onto the stars. The grid is much larger. So most of the grid, there's no matter. And we do all of this with dg, so it's efficient. And then even doing the merge, DG is still used in portions of the merged remnant. Only when it becomes close to becoming a black hole, DG can no longer be used inside the matter. There's also load balancing I should talk about, because as we have seen, we have this dynamic AMR and switching between finite volume and DG. And as I've just talked about, the finite volume elements, they use more points, like twice as many points per direction. That means really 8 times as many points. And that means the evolution step in a finite volume element is a lot slower than in DG. But DG is more efficient in the sense it can deal with less points. But Nmesh keeps switching between DG and finite volume. And this is done locally at each MPI, within each MPI process. Also, the stars move. That means the AMR has to refine certain areas and de-refine other areas. But these, and again, the refinement is done locally within each MPI process. That means if one MPI process now starts refining, it has more domains suddenly, and maybe it switches to finite volume, and then it has even more points. Yeah, so there you can see that even if the load is perfectly balanced in the beginning, after a while, each MPI process will have a different load than before. That means it has more or less elements than before. So what you get in the end is you get a very unequal workload after a while. And that would mean that some MPI processes have less to do, and that means they are done already with an evolution step, while the others are still working on their evolution step. And that means some of them would have to wait for the others. And this sort of load imbalance is bad. It's something you wouldn't have because some of them are sitting there idly. And the solution that we have for this is that each element that we have here has a timer that simply measures how long a time step takes. And then basically each MPI process knows how much time it's spending in the calculation. And then the MPI processes can compare amongst themselves how long they actually take for an evolution step. And then we can redistribute the load. And since the stars on the evolution timescale, they don't move, they just move a little bit in one step. So the load doesn't get out of whack immediately, the load balance, but after a while. So basically what we do every few minutes in real time, we rebalance. And that we basically do, we compare these timers and see how long has it taken. And then we see that some MPI processes have less to do than others, and then they get sent some elements. And this way, things are sort of more well balanced. Okay, so this is basically what we do for load balancing, which, as I said, is really necessary when you do AMR and if you switch also between finite volume and DG all the time. So, so now here's the summary. So we have developed this new Nmesh program. And in some test cases, we have done not all that many yet, but it shows very good, strong scaling results. And we can successfully simulate single neutron stars with the discontinuous Galerkin method alone. But if you have true shocks or star surfaces, it's often better to use finite volume methods. And for this, we have various ways. We can switch to finite volume or finite differencing methods in non-smooth methods. This is one way. Or we can just use DG alone with certain limiters. But as I said, these limiters work sort of less well. So our preferred solution would be to use finite volume in non-smooth regions, which means that actually we have all the necessary ingredients to do evolutions of neutron star binaries. It's really what we want to do in the future, right? What we have done so far are only certain test evolutions. We haven't done any real physics. All the real physics we are doing is still done with the BAM code for our group at least. But we are getting sort of well prepared now to sort of switch over. So that's basically all I wanted to say. So if you have questions, so please ask now. Thank you very much.
Well, thank you. So are there any questions, Zach? Or do we need to pass the microphone?
Yeah, I didn't hear anything.
Okay, hang on. We'll pass the microphone.
Yeah.
Can you hear me now?
Yes, I hear you.
Yeah. Yeah, I mean, this is super impressive stuff. I did have a question. So back in an earlier slide, when you were showing the difference between a finite difference versus the sort of DG mesh, very early on, just a one-dimensional, the one-dimensional plots basically.
Oh, let's see.
Yeah.
This?
There it is. Yeah. So I appreciate that, it is standard practice in finite differencing to use a uniform mesh. And I also appreciate that it's a bit simpler. But I also wonder if there might be a potential improvement in accuracy if you use the same grid spacing for both finite difference and the DG methods.
So we haven't tried that, but I can't imagine that this is actually a good idea, because when you suppose you use the same number of points and you just spread them around unequally, like in the blue element, right?
Yeah.
What do you gain by that? I would say you gain practically nothing, because you still have to use a finite differencing method of a certain order, right? Maybe use second order accurate or something like this. That means the error will still be second order accurate, but you then, if you actually check this, if you go through the calculation, the error term that you're getting in any method that you're using in finite differencing has a coefficient in front of the error term, and the coefficient is actually larger when you have unequally spaced points. So that means you're not actually gaining anything in that sense. You're just losing something.
I mean, the point of having like a Gauss-Lobato kind of spacing is to reduce the incidence of the Runge phenomenon. And I wonder if that sort of basically what you would be doing is applying kind of a type of filtering by doing an unevenly spaced and filtering potentially consistent. Also, by the way, you could, in that case, probably get away with a super high order finite difference or a higher order finite difference without the worry of introducing noise, for lack of a better term.
So I have to say we have not tried that at all, because, as I said, I was thinking that the actual error terms are larger. But you're right, maybe it helps with oscillation. So this is maybe something worth exploring. Have you ever tried anything like that in one of your codes?
I mean, unevenly, I have not, I have to admit, but unevenly sampled grids, it's just a matter of computing the finite difference coefficients, and then things should just work.
Oh yeah, I mean, I completely agree that this differentiation matrix, I can set it up, but it's not an issue to do all that.
Yeah, but I am curious if it might help with noise and whatnot.
Okay, I mean, at least it's an interesting idea now that I understand it better. Okay.
Yeah. Cool. Yeah, and by the way, so the second question, why didn't you just do Z4 from the beginning? Is there a reason?
Yeah, there's a reason for that. The DG method needs the evolution system to be of that form, sort of, meaning it needs to be first order in space and first order in time. And the usual Z4 system is second order in space. So you can't actually use it with the DG method without sort of modifications of either the DG method or of the system itself. And this is what we're planning to do in the future. We will either modify the DG method so that it can deal with second order systems, or we will introduce a first order version of the Z4 system.
I see. Interesting. But maybe if you had the finite difference grids on the same grids as the DG, you could do DG. You could just use the same grids and just use DG on the hydro and finite difference on the spacetime without any interpolation.
I guess you could, yes, if you have the same grid. But I mean, for the spacetime, you'd probably also want to, in this case, you would want to use DG and not finite difference, because DG is probably more accurate for the spacetime, because the spacetime is probably smooth.
Yeah, but I think an 8th order finite difference could do pretty well as well. But yeah, fair.
Yeah.
Cool. Yeah. Thanks, Wolfgang. Very, very interesting.
Okay, thank you.
So I think Roland had a question. I saw his hand up.
Right.
Sure.
So Roland, go ahead.
My virtual hand. Can you hear me?
Yes.
Okay. Let me see. What did I want to ask? Yes. When you do the rebalancing of your DG elements, or just the elements every couple of minutes, so you have millions of elements and you rebalance every minute or so. I recall from finite volume schemes that this rebalancing is actually fairly expensive if you have many elements. Do you find that you have to be careful how often you do the rebalance and redistribution of data, and where do you cut them so that you have the smallest number of surfaces between processors?
So we haven't done any of these things yet. So basically, for this simulation that I've shown you, we actually didn't have millions of elements yet. It was just hundreds of thousands, and there it wasn't a huge issue. We haven't actually tested if you had more, what would happen. So my honest answer is we haven't tried it, how bad it gets. What I can say, when we just have hundreds of thousands, it's not a huge cost if we do it every few minutes.
Okay, thanks.
So, Wolfgang, I also have a question. So, when you do the switching between your DG and finite differencing or finite volume, I mean, you're changing the number of grid points, so you have to map your solution in some way. How do you do that?
Oh, we use very simple interpolation. I mean, you know, for every of these grids, you can do interpolation.
So does that affect your accuracy if you use sort of a low order interpolation? Because I mean, you are working on points where you say you have trouble, so I assume you probably use a low order interpolation something.
Yeah, if we actually have trouble, if we are in the finite volume region and we now want to interpolate onto something else, then we use some sort of Vino interpolator. But this is basically, and this Vino will detect if there's a shock or not. And if there isn't a shock, then it's still a relatively high order. Then I forgot what the order was, like 6th or 8th order. It's not so bad. But if you have a shock, this of course drops. But the bigger problem we have with this interpolation is that we don't use any sort of sophisticated interpolation, but we just use the regular interpolation that you would, the easiest way you would think of, so to speak. And if you interpolate from a finite volume to a DG element, you actually sort of violate mass conservation a little bit. But it gets better with resolution, but there's a little bit of a violation. And this is, I think, my bigger worry, that we have a certain amount of mass conservation violation each time we switch. Again, it should go away with resolution, but it's at least something to think about. So this is what I worry more about than sort of non-smooth features, because as I said, when we're in a DG element, it's smooth anyway, and then the DG interpolation is extremely accurate. But the finite, what you mentioned with finite volume, that it uses very few points, well, that would only happen if there's a shock, and then the accuracy is anyway not so great.
Okay, thank you. Any further questions? Maybe you'll come here to the microphone since you're not very mobile.
Hey, Wolfgang, thanks for the talk. I have two questions. The first one is, after like all the switchings, you know, from different methods, what's like the overall conversions you get with this in the end?
So for this round, that's what we have. The overall conversions order is hard to say. From this, I mean, it looks more than second order conversion, but we have only 3 resolutions. I need more resolutions to really honestly evaluate this. But you can see there's a change from blue to orange, and then that sort of, I mean, this should be a flat line. So if you look at the error in the green is a lot less than in orange. So the error goes down tremendously when you go down, when you go up one level of refinement. While here the error doesn't go down so much. So it's a little bit hard to say, actually.
All right.
This could be a problem in the future, that like when you have a finite differencing or finite volume code, the convergence order is very well defined. Here now we are switching between different methods, and the finite difference method, you know, I've shown you that for smooth fields it should be second order. So you have a second order method, but then together with a DG method, and you don't control very well where you use what. So I'm not entirely sure what the order of conversions will be.
I see. And the second question is probably naive because I don't really know the DG method well, but as I understand it, basically under the DG method, your differential matrix is like a full, completely dense matrix, right?
Yes. Mm-hmm.
So for every element, basically, if you want to approximate the derivative of a field in an element, you are considering the influence of all other elements in your domain to find the derivative of that element.
No. You're considering all the grid points within an element, but not the other elements. It's local to the element.
Oh, okay. It's local to the element. Got it. Yeah, that basically was the question. Thank you.
Okay, okay.
Well, I think we're out of time, so thanks, Wolfgang, again.
Okay. Okay, good.
And it's now time for coffee break here, so we meet again at 10:30.
Okay.
Thank you
Okay.
very much.
Thanks. Bye-bye.